All right, here's an energy problem that kind of describes why you have a ramp or you want a ramp when you run a U-Haul. So I'm going to blow this up a little bit. So here's an ad, okay, from U-Haul, and it says, okay, that this is going to provide you a 50% easier loading, okay? Now, one thing that helps with that is the ramp. So let's figure out what's the whole purpose of having the ramp. All right. Now, so picture number one is, let's say you're trying to lift the box up into the truck, there's no ramp. Versus here's the back of the truck, this is the tire, okay? And then here's a long ramp. So if there's no ramp, okay, now when you lift the box up with your hand, you're trying to do work against gravity, okay? So I want to find the work done by gravity to put the box in the truck. Okay, so again, so you're lifting this thing up, there's your hand, okay, so you're pushing up. Okay, so you're fighting the gravitational force. So as long as you do that slowly, okay, so that you raise it up at constant speed, if the box weighs 50 pounds, you just have to push with a force of 50 pounds. So you just have to exert the force mg. So I want to find the work done by gravity to put the box in the truck for picture one. Whoops. Okay, so while it's going up, okay, remember mg points down, you're moving in that direction. H is the height from the floor or from the ground to the edge of the truck. All right. So the work done by gravity is the force mg times the distance it moves times the cosine of the angle between them. So remember, mg points down, you're headed upward. The angle between mg and the direction you're going is 180 degrees. Cosine 180 degrees is -1. So that's the work done by gravity, minus mgh. Okay. But the work done by you, okay, to fight that gravity is positive mgh. So the work done by you goes into increasing or changing the potential energy. So now when this thing is sitting here up here in the truck, you gave it, with respect to the ground, a potential energy of mgh. So the work done by you is mgh. Okay. Now, let's say you can use the ramp. So here's picture number two. Here's the back of the truck, and you want to put the box in the back of the truck using the ramp. Okay, so the length of the ramp is d, and we're ignoring friction, all right? So you're going to start here. You're going to push the box up, all right? And I just want to find the minimum force. Obviously, you have to just balance out the force of gravity that's trying to bring it back down. So you're just going to move this up at constant speed. So I drew the forces. You have mg, okay? And I mean, I could draw the normal force. I don't need that, but there's a normal force, all right? And I broke up mg into its components. I have mg cosine, I have mg sine, and then I put two little lines through mg. And theta is the angle of the ramp. Okay, so now the work done by gravity is mg sine theta. Okay, that's the component of the force of gravity that's doing work. Okay, this component mg cosine doesn't do work because the box is moving in that direction at 90 degrees to mg cosine. So only mg sine right there does work. So I calculated the work done by gravity to move the box along the ramp of length d. So work done by gravity is the force on that picture. There's your mg sine theta right there. So there's your force. Length of the ramp is d, and the cosine of the angle between them. Okay, so you're headed down, or sorry, mg sine theta points down. You're moving upward. The angle between those 180 degrees. So cosine 180 is -1. So the work done by gravity is minus mg d sine theta. I just put the d in front here. Okay. Now, what is d? Well, if I look at the ramp, I just redrew the picture here. That's the length. D is the length of the ramp. H is the height from the ground to the tip of the truck. So if I ask, well, what is this d sine theta? Well, here's the triangle. Sine of theta, so sine of theta, is opposite over hypotenuse. Okay, so my opposite is h. So opposite over hypotenuse. So I multiply both sides by d, okay? So I multiply both sides by d, and h is d sine theta. So right here where I have d sine theta, that's just h, okay? So we found that in picture one, where I'm just lifting it up, I didn't rent a ramp, okay? Okay, the work done by me, I'm sorry, the work done by gravity is minus mgh. Here, if I rent a ramp, the work done by gravity is the exact same. So if I don't rent a ramp, that's how much work I have to do, mgh. Okay, if I rent a ramp, how much work do I have to do? The same amount. So what's the whole purpose of having the ramp? Okay, because the change of potential energy is the same. Start with 0 on the ground, okay, and potential energy when it reaches the truck, okay, change of potential energy, okay, is mgh. So what's the whole purpose of the ramp? Okay, if I don't have a ramp, okay, in picture number 1, okay, what force did I need to lift the box? Well, I just had to fight the gravitational force. So if the box weighed 50 pounds, I'm sorry, the box weighs 100 pounds, I have to apply 100 pounds of force to lift it. So the minimum force that I had to apply was the weight of the box. Okay, with the ramp, okay, the force that I had to fight was mg sine theta. Okay, so that's a much smaller force than the entire weight of the box. So I put in some numbers here. Okay, so let's say you're trying to lift a 100-pound box. Okay, so about 445 newtons. So you have a 100-pound box. Okay, so if I don't rent the ramp for picture 1, I have to lift that box up. Okay, I have to lift up the 100-pound box all the way up to the edge of the truck. Okay, so that's the force I have to exert. But now up here, if I rent the ramp, okay, for that same 100-pound box, okay, all I have to do is I just have to push at that force of mg sine theta. Okay, well, there's my mg, that's the weight of the box, 30-degree ramp, sine of 30 degrees in your calculator is a half. So I only have to exert 50 pounds of force. Okay, so in this first picture, 100-pound box, I have to lift 100 pounds. I have to exert a force of 100 pounds. Over here, I only have to exert a force of 50 pounds. So that's the whole purpose of having the ramp. You actually reduce the applied force. So that's why I think in the earlier chapter I showed on the Wikipedia page on simple machines that the inclined plane is a simple machine. It allows you to change the force, okay? Meaning instead of lifting it up at 100 pounds, I only have to exert 50 pounds. So that's why way up on the top it said, oh, you can reduce, what does it say? It reduces, okay, 50% easier to load. Okay, well here, you're using 50% less force. Okay, now what if you even had a longer ramp? Okay, you spend the extra money, you get the really long ramp. Okay, well instead of, there's the truck, okay, instead of the short stubby ramp, now you have the long ramp. So that means instead of having a tall angle, big angle, you'd have a small angle. So let's say this angle is only 15 degrees. Okay, well the force that you have to push, you have to fight that mg sine theta. So it's mg sine of 15. So on my calculator, I put in my 100 pounds, sine of 15 degrees. It's only about 26 pounds. So the whole purpose of the ramp is instead of lifting the box all the way up here, that 100-pound box, okay, yeah, you have to move it further, okay, instead of a couple feet, okay, now you have to go a far distance, but it requires much less pushing force. You only have to exert 26 pounds of force to move it up to the truck.